FACS meeting. This is our main meeting of the year, the Peter Landin Semantics seminar. We've got a speaker lined up here. Just before we do that, I'm going to do a little presentation, which hopefully is a small surprise. So the BCS do these awards for people who've done outstanding work for the BCS. He doesn't know he's done outstanding work yet. But Tim, would you like to come up and accept a certificate of appreciation for the BCS for your long-standing service? Tim's done lots of work for the FACS over the decades, I think, including being chair in the past. He's also currently the newsletter editor, continuing doing that. So we're all very grateful to you, Tim. This is a small, well, something to put on your wall somewhere. We can have a little picture. You can say a few words if you like. Somebody is there, the photographer is there.
Well, thank you. This has come as an enormous surprise, I must admit. I've sort of been involved. Yes, I remember joining the BCS shortly after I graduated in my first job, and the annual subscription was £1 a year.
Now you know how long service is.
About 9 years later, I was no longer eligible for the sort of recent student rate, and they put the rates up anyway to £9 a year, and I thought, this is too much, so I resigned for a bit, and then I rejoined quite a lot later, and so you've even got these letters after my name.
Yes,
because you've been most assiduous.
Yes. Yes. We expect to see it behind you in all your Zoom calls. Anyway, thank you very much for all the work you've done for FACS over the years too. Well, now we move on to the Peter Landin Semantics seminar. We have Nicholas Wu to give the talk. As you know, we try and tie this in with something to do with Peter Landin, which is doing very nicely. He did do his DPhil at Oxford, and then was a postdoc there, then became a lecturer at the University of Bristol. Is now at Imperial College, where he leads the functional programming group, so that's very apt with Peter Landin, and he's come up with a particularly apt title, which I'm sure some of you may recognise, the next 700 domain-specific languages. So I'll hand over to Nicholas.
Great, thank you. Yeah, well, thanks so much for inviting me to come and speak here. So it's been quite fun actually preparing this talk because it's the Peter Landin seminar, and I wanted to make it have lots of historical content. In fact, it's got more historical content than anything else. And as I proceeded to prepare this, it became more and more historical. So, as you said, I lead the functional programming group, and Peter Landin was, I think, at heart a functional programmer, and that's very clear in his work. And so it's quite fun to sort of dig out where all that came from. And so I thought I'd start with this sort of perspective that there's this distinction between functional programming and imperative programming. And as an undergraduate, I thought these were two completely different worlds, but I didn't really know where they came from. And of course, we now know that, or we've known all along, that the functional world came from Alonso Church, and in some sense, the imperative world came from Alan Turing. And so this talk is a dive into some of the history that's there. I'm sure I'll make some historical accidents and mistakes because history is difficult to uncover from papers alone. So I'm sure there'll be people in this audience who are going to correct me in some of these details, and I'd love to hear more about this later. So let me just start with things that happened before computers, and let me transport you back in time. The year is 1666. We're still in London, and this is what it looks like. There is fire everywhere. It's the Great Fire of London. What a catastrophe. So let's just move away from London and go closer to where Leibniz was. So Leibniz in 1666, came up with the published version of his dissertation, the Arte Combinatoria, the Art of Combinatorics. And in this thesis, he presented all sorts of interesting things. He starts off with an argument of the existence of God using just axioms and logic. And from there, he kind of decides that what he wants to do is create an alphabet of all human thought and of all human ideas, because his big thesis is that ideas are just, ideas and concepts are just built out of smaller ideas and concepts. And by taking combinations of these things, we can start reasoning about, well, things like philosophy, but things like the truth, etc. So in this article, so Leibniz was a prolific writer. I think he wrote something like 15,000 different letters, spanning over something like 60,000 pages. So it really is quite difficult to find his works. So people have sort of put letters together and things like this. And one of the things that he said was something like, when trying to get from England to Holland, I was detained for some time in the Thames by adverse winds. During that time, knowing not what to do, and having nobody in the ship except sailors, I meditated on things, and especially thought about my old design of a rational language. And then he said, for if we had such as I imagine, we could reason about metaphysics and morality, just like we do about geometry and analysis. And of course, he later went on to design a kind of calculator, which allowed him to mechanically do things, and he thought it was such a shame that people were being used to do calculation when clearly machines could do it. And I think in some other works, he says something along the lines of, if I just had a few good men and a few years, we'd be able to crack this and have the mechanization of all human thought. And then later on, he realizes that was just far too ambitious. But so this is, 1677, so it's quite a long time ago. And he says, for if praise is given to men who have determined the number of regular solids, how much better will it be to bring under mathematical laws human reasoning, which is the most excellent and useful thing we have? So he's really thinking about logic and how we can mechanize that, or at least how we can make it more symbolic, so how we can reason about it carefully. Okay, so let's fast forward quite some time. We're going to Germany still. So we've got Emil Dubois Remo. Now I don't know much about this man. I think he was a physician. And he was presenting to the Congress of German scientists and physicians. And he says, ignoramus et ignorabimus. We do not know, and we shall not know. He was referring to the fact that there are a whole bunch of things that we simply have no chance of understanding. So for instance, the fact that we are human and that we can see and perceive, and what is this experience that we're all having right now? That's just something that we don't even come close to understanding. And yet we have to put that together with the fact that there seems to be a physical world. How can we put together the fact that we have this world of things that we perceive and the physical world together? There's no way of understanding this. This quote, I think, tickled or maybe annoyed Hilbert. So Hilbert in 1930 responded to the same Congress with "Wir müssen wir wissen, wir werden wissen." We must know, we shall know. And what he was saying there was actually not about psychology or about the human mind or the human existence, but rather he was talking about mathematics, and he was talking about the fact that there must be a place somewhere where we can be sure of the things that we know and that we understand. There must be somewhere where we can trust all of the truths and be able to ascertain everything that is true in that particular world. So in 1928, he and Ackermann write the Grundzug der theoretischen Logik, so the groundings of logic, and there they formalize the Entscheidungsproblem, the decision problem. And this is the problem that says that given a reasonable logic, there must be a way in first-order logic to ask a question, and surely there'd be or is there an algorithm that answers just yes or no to that particular logical proposition? So in Hilbert's mind, I think even up until the late 1930s, it was clear to him that everything that we could reason about could be discovered through some process, through some algorithm. So his hope was that the answer to this problem was yes, there's a way of solving the decision problem. Now, as we all know, there were quickly problems with this particular formulation, and I think the problems began with Gödel, who showed that any reasonable system of logic has true statements in that system that, despite being true, cannot be proven to be true within the system itself. So he writes about this in 1931. And not too long after, but there's still this question, which is, okay, so what Gödel proved was that within a system, there are statements that are true that can't be proven to be true within that system, but that doesn't really solve the decision problem. Maybe if the decision problem holds true, there could be an algorithmic way of, given a logic, working out whether or not things are true from the outside, or using some kind of algorithmic process despite not being embedded into that particular object. So maybe the decision problem isn't settled. But then, of course, Church and Turing both answer no, there's no such algorithm possible, and they do so in two different ways, two independent ways in 1936. And my understanding is that Turing was slightly scooped by Church. He didn't, of course, they didn't realize that the other was working on this problem, and was somewhat disappointed by not getting there first. But nevertheless, I think they made up for it. I believe that Turing was looking for work at the time, and didn't manage to find anything at Cambridge where he was, but Church offered him a PhD position with him in Princeton, which he then accepted, so off they went and did some research. Later, of course, Church and Turing get together and they show that there's a correspondence between what they did, and that's great. So let's dig into what Alonso Church achieved. So he introduced the lambda calculus. So the lambda calculus in 1932 is really a calculus about bindings and substitutions, and it's a means of doing calculation, it's a means of doing computation that's purely symbolic. And instead of writing things like, let's see if I can do this. So instead of fx equals 5x plus 3, we can isolate the f by itself on the left-hand side by pushing the variable x to the right-hand side, binding it under a lambda term, and then copying out the body of the expression. So that's the idea behind a lambda abstraction. It's just a way of having an anonymous function. And then in a paper in 1936, he starts talking about what could be effectively calculable. So by that, he's thinking about what is it that we can reasonably calculate with this system? What are the terms that we can prove within? And so he talks about, he introduced the idea of Church numerals. So Church numerals are really this idea that you've got a way of encoding all of the natural numbers by having two variables. So there's s and z, so s for successor and z for 0. And so the number 1 is the successor applied to 0 once. And then the number 2 is s of sz, so that's 2 successors and 3, etc., etc., etc. And so addition of n plus n, well, if we decide that natural numbers are always functions of the form lambda sz to body, then n plus n can be given s and z. We apply m. So m is going to take in a function that's going to do successive s many times, m many times, so that's s, and then applies that to its version of 0, which in this case is n sz, so n lots of suc over z. And then, of course, this is also a lambda term because we can push the values m and n to the right-hand side, and so we've got addition encoded inside the lambda calculus. So you can do this with basically everything that we like, so all data types can be encoded in some way using Church encodings. So I've read as I've been doing my research over this talk, I read that I think it was Kleene had a conversation with Church about the unsolved problem paper, and Church, I think, just quit. Oh, hang on a minute, I think this has something to do with the decision problem, and then basically wrote the paper. And so if you look at the paper, a note on the Entscheidungsproblem, it's very short. It's only about 4 pages long. And it just starts off with, in a recent paper, by which he's referring to this one here, I proved that there were things that were effectively calculable. This is what they're like. And now I'd like to extend that to say that there are certain things that we can't do and prove that the decision problem can't be solved. And he does that by converting, by showing that converting an arbitrary term A into a term B is simply not possible. So you can't do the equality between two lambda terms in this way, and that solves it for him. So it's quite a quick paper, but it builds on the foundations that he's been laying for quite some time. On the other hand, you have Turing's work, and so he comes at this problem from a completely different perspective. And I think at this stage, it's not exactly agreed upon whether Church actually solved the decision problem. So his notion of effective calculability may or may not really correspond to what we think of as a means of writing algorithms. People weren't really sure if that was adequate. So is the lambda calculus really the way we want to describe algorithms or not? Wasn't really an answerable thing. Turing attacked this problem from the idea of having, of course, these Turing machines. And in his paper, he doesn't call them Turing machines, of course, he calls them A machines for automatic machines. And he calls A machines that work on binary numbers, I think they're called M machines, or sorry, the computing machines. The 0 ones are the computing machines. And this is the part of the paper which makes the famous halting problem statement. So he says we can show further that there can be no machine, I think that's an E, which when supplied with the description of an arbitrary machine M will determine whether M ever prints a given symbol 0, say. And so he goes on to prove this. And I think what made Turing's result compelling for the academics at the time was that the machines were so simple. They had finite states, they had infinite tapes, and they were just working along this, doing calculations, and he was able to show that you can do reasonable things with his machines that correspond to how we might want to solve problems algorithmically. So this was accepted as a good answer to the problem, although it was not that Church's was not accepted. I think this was there was more trust in this one. The question, of course, is whether or not Church and Turing's work correspond. And at the back of Turing's paper, there's an addendum that basically says, after the initial publication of this, here's a little proof or a sketch of a proof that the lambda calculus and Turing machines are equivalent. And it's just a sketch which is then turned into a proper paper at a later date. But at least it's clear in Turing's mind that these things are equivalent even at this early stage. So yeah, it's a kind of a quick quip at the end of this paper that there are some important implications, in particular that the decision problem has no solution. So he showed that there was an encoding between the halting problem and the decision problem, and so because he proved that the halting problem was solvable, the decision problem wasn't solvable as well. Okay, so that's the pre-computer days, and I'd like to now point out John von Neumann's play in this. So von Neumann was at the time considered a truly remarkable genius, and we see people talking about comparing him to the likes of Einstein and other great mathematicians of the time. They say that von Neumann's mind was absolutely brilliant and completely sharp, and they've never met anybody like him, and he's better than the contemporaries at the time. So he was apparently a remarkable man, apparently also a very wealthy man, and was given a professorship at a remarkably early age. I think he was something in his 30s when he was given a full professorship. Was then asked to lead the way towards the mechanization of computers. And he based his design, the so-called von Neumann machine or architecture, which we now accept for computers, essentially on the Turing machines, except that the difference is where Turing machines work with infinite tapes, we don't have access to infinite tapes on our machines. We have access to finite array-based machines instead, with constant lookup access rather than having to scan through these things. But essentially, all of the components of the von Neumann machine come from Turing machines. So the report that you see here is the first draft report on the EDVAC. The EDVAC was an American computer that was, I think, first built in around 1949. I think the dates are a bit shaky and arguable at this point. It's difficult to track back exactly what people say when what happened. And the EDSAC was actually built before the EDVAC by the British, using the report on the EDVAC that was designed for the American machine. So they got there first. But I think it was probably all secret at the time. So that's quite funny that given the report he wrote, somebody else managed to get there beforehand. So those were the early computers. And I think it sort of lays the foundation of what we then went on to do in terms of programming. So the first, let's say, serious programming language is, of course, Fortran, developed by John Backus. In around 1954. So it was targeting the IBM 704 machine, and there's a picture of it down here. And what we're looking at is an excerpt of the Fortran report, which shows a sense of what's going on with Fortran, the language. So we've got things like rewind 3, then do 3, I equals 1 to n, and then you've got these the if then else statement is interesting because this isn't an if then else statement like we recognize today. This has an if, then a predicate, and then 3 numbers corresponding to the number of the address you jump to if the comparison of the expression is negative, a number to jump if it's 0, and an address to jump to if it's positive. So this is not a conditional expression, how we'd understand it to be. This is really just a jumping sequence. And of course, gotos are absolutely normal at this stage. It's very, very much based on the way the computers work. And we're not thinking about control operators basically at all at this stage. Backus writes later on in an article, so in 1979, a sort of retrospective on his work. He says, much of my work has come from being lazy. I didn't like writing programs, and so when I was working on the IBM 701, writing programs for computing missile trajectories, I started work on a programming system to make it easier to write programs. And he also says, most people think Fortran's main contribution was to enable the programmer to write programs in algebraic formulas, because Fortran is the formula transformers or translation machine. A language, but instead of machine language, but it isn't. What Fortran did primarily was to mechanize the organization of loops. So this is what Backus thinks of as a language. And it's interesting that later on in his life, Backus becomes essentially the leader of a new functional programming group and moves very much away from the imperative world and starts thinking about how you can do things functionally. So it's a win for people like me. So very shortly after, Lisp in 1958 came out. Lisp is a completely different language. It's based on Lisp processing, and from the beginning, McCarthy, in the first programmer's manual, they describe Lisp in terms of lambda terms. So he's saying if epsilon is a form in variables x1 through xn, then lambda x1 through xn, epsilon will be taken to be a function of n variables, and so on and so on. So lambda expressions are at the heart of Lisp right from the very beginning. So it's based on lambda calculus. And interesting that here he has a very different way of thinking about conditionals. So he says we have a conditional as being a number of propositions P1 through Pn with arms to the right, which will be E1 through En. And if you evaluate them in turn, the first one that's true is the one that you go to the right and use that as the value of the expression. So this is much more like what I understand to be a conditional expression. It's not involving jumps, but rather it's saying, if in this branch something is true, then we have this thing on the right-hand side as being the result that we want. He also talks about how you could use conditional expressions to define something like a factorial function. So here he's thinking, of course, about recursions right from the beginning, and he's saying n factorial equals, if n is 0, then return 1, and then instead of writing otherwise, he writes true, because these conditional arms are evaluated left to right. So the first one that's true is the one that gets executed. So if true is the last conditional that we go for, so otherwise we do the recursive n times n minus 1. So that's how we work where we compute that. And from my perspective, it's interesting that he uses higher order functions as well in this very first report. So here we have the description of functions with functions as arguments. And it's a function called maplist, which given a list x and the function f, well, if that list x is null, then we return nil. Otherwise, we cons on the result of applying f to the value x, and then we continue recursing with maplist on coulda xf. What is this strange coulda? Well, in Lisp, the implementation of lists is in terms of two operations, one called car and one called coulda, where car corresponds to the head of the list and coulda corresponds to the tail of the list. Rather than using the words head and tail, car and coulda were used because car corresponds to the address part of a register, and coulda represents the decrement part of a register. So there's your A, the address, and your D, the decrement parts. And this was just a very convenient way of working with lists that was fairly efficient in the system at the time. And so there are some peculiarities about Lisp which are very much tied down to the actual architecture of the 704 machine, like this. There was even notation for being able to take the head of something that's down the tail. Something like tail, head after tail would be something like CADR, and then you could iterate the number of Ds to go further down and do strange things like this. Okay, so one way to think, or the way I'd like to frame this, is we've seen the imperative and the functional worlds right from the beginning, and it's nice to see that they come together again very shortly after in the creation of Algol. So this is Algol 58, which was developed by a committee of people, by probably the greatest programming languages people at the time. So there's Peter Noir, John Backus, McCarthy, and a whole bunch of other people that sit down and write this language. And apparently the meetings were full of arguments, and people were not happy about the features that were coming in or out of this language, but eventually they managed to come to an agreement about what this language should be like. It introduced things like iteration and recursion. Recursion was a very controversial idea to have in the language at the time. People objected to whether that should come in at all. It had the distinction between assignment with colon equals and equality. There were the ideas of code blocks and lexical scope. There were nested procedures, procedure parsing as well, so there were higher order ideas there as well. There was the invention of BNF, so Bacchus and Law form for the description of grammars. It came out through the development of Algol, and Algol also had a distinction between call by name and call by value as well. And so here's an excerpt from the first report on Algol of a procedure, which takes the absolute greatest element of a matrix, and it sort of shows that you have things like assignment, you've got for loops, and so it's a much more sophisticated language than we have in Fortran. And this example doesn't really show it, but you can have much more expressive right-hand sides of equalities where you're actually doing some arithmetic on that right-hand side. We're thinking much more algebraically at this stage. Tony Hoare was taught Algol by the hero of this seminar series, by Peter Landin, and he was delighted to see a language with recursion where he could actually implement quicksort. And his comment on this in a paper in '74, his hints on programming language design, he says, that Algol was a language so far ahead of its time that it was not only an improvement on its predecessors, but also on nearly all its successors. So that was a fun thing to say. So what happened with Algol and Peter Landin? So, Landin was working on the lambda calculus in 1964 and wanted a means of evaluating lambda expressions in a machine. So he writes a paper, this is the mechanical evaluation of expressions, where he introduces the idea of applicative expressions. So these are the AEs, as he calls them. Applicative expression is essentially just syntactic sugar for lambda expressions. So here we have an applicative expression and we have a lambda term, and they're essentially the same if you just scan from top to bottom, except rather than having lambda bindings, you have let statements, and you have this distinction between lets and let recs, where a let rec is one that's a recursive let statement, where in the lambda calculus you would have to use the Y combinator to do recursion. So there's a clear distinction between these things. And these days, we don't tend to, in languages, make the distinction between things like lets and let recs or where and where recs. We simply assume that everything could be recursive and move on from that. But in this early paper, there is a clear distinction between the two. The machine that he used to evaluate the lambda calculus is the SECD machine, which was really the first abstract machine for doing this, and has been important ever since in terms of understanding how the lambda calculus can be executed. In 1965, he writes this paper called A Correspondence Between Algol 60 and Church's Lambda Notation, part 1. There's also a part 2 coming up the year after, so hold on for that. But he introduces in this paper the idea of the so-called imperative applicative expressions, which is basically where he has this notation for lambda calculus, but adds an assignment operation. And that assignment operation is what he uses to fully demonstrate how the Algol 60 corresponds. And interesting here that procedures in Algol 60 corresponds to lambda expressions. So that's the part that makes this paper work. And so it's nice that we have that even Algol is actually a functional programming language according to Landin. So that was an important paper, but probably the paper which has the most catchy title and the one that this talk is named after is, of course, the next 700 programming languages, which was written in '66. Just 300 years after Leibniz had his dissertation. So this paper is interesting because it introduced a new language called ISWIM. ISWIM stands for If You See What I Mean. And If You See What I Mean was a language that was never really implemented. So he talks about it as being an unimplemented language from the beginning in his abstract. It's the very first line of what it says. But it's curious because part through his paper, he talks about early experiments and prototypes of this language. So I think he probably did have an implementation that he probably wasn't proud of demonstrating, but it's unclear to me at this stage. And one of my colleagues told me that later there were some languages based exactly on ISWIM, so languages like Lucid, but they came much later. Why was this paper so influential? Not just the catchy title, which he says in a footnote, he could have called this paper Church Without Lambda instead. So why Church Without Lambda? What does he introduce in this paper? Well, he introduces mathematical notation for functions and lambda expressions using let and where constructs instead. So very much in the flavor of what we just saw in the elliptic expressions paper. He wants there to be indentation to separate clauses, and talked about the offside rule as a way of saying where the indentation starts for subclauses or subwheres. And he has a distinction between physical and logical languages, and he goes into a lot of depth about this, which we'll talk about in a minute. He talks about how we should interpret languages through layers of abstraction linked by syntax, grammar, and denotation. His language should be a garbage collected language. He wants equivalence between terms to actually be equivalences. So he's thinking about using calculational reasoning to prove that one program is equivalent to another program. There's no explicit sequencing in this language. And he even has ideas that are not explicit of algebraic data types coming up in this paper. So a paper absolutely packed with new ideas and a really interesting read. So why does he call it Church Without Lambda? Why is that the alternative title? So he really wants to talk about where notation in this paper. He thinks it's much more convenient than lambda terms. It's the way you really want to write functions. So he writes things like this. So you have u minus 1 times u plus 2, where u equals something. And that's much more convenient in this lambda term here. And then similarly here, you've got a different expression where you're not just defining one variable u, you're defining two variables u and v. And you write the word and. So he's really thinking about the human being involved in this process, rather than having to translate things into some kind of lambda expression. Why aren't we just writing the mathematics like we would like to write mathematics? Actually, I'm slightly lying to you. These examples aren't coming from the Next 700 language, the Next 700 programming languages paper. It comes from the previous mechanical evaluation of expressions paper. But there he's using it as an informal language. And the 700 paper is where he thinks of it now as being an actual language, which we should give a semantics to. The next example is, of course, where he uses where rec instead of using the y combinator and lambda expression. So he thinks that it's much easier to write these things. And we also have the if then else expression coming up, very much in the form that McCarthy had introduced. So we've got McCarthy conditionals as given in this language. One thing that we don't see so often today is actually his use of where expressions for types. So types were around at the time, people very much knew about them. Landin decided that he didn't really want us to write something like integer n. He suggested that perhaps we should write something like where n equals around n instead. So thinking that round numbers are of course integers, so why would you have types hanging around when you could talk about round numbers instead? So that was an innovation that didn't make it through, I don't think. And there's a very charming discussion at the end of this paper. I mean, for those of you who've read old papers, it used to be that the discussion after a paper was presented was written down and put into the appendix of the paper itself. And so you have this wonderful discussion between Landin, Christopher Strachey, Peter Noir, and a whole bunch of other people talking about the existence of should we talk about declarative languages or functional languages? What are they exactly? And Peter Noir says something like, regarding indentation, in many ways I am in sympathy with this, but you would regret it because of the kind of rearrangement of manuscripts done in printing. And they had a whole debate about how annoying typesetting is and how the editors will keep changing things. And Peter Landin had to go through 4 variations of his submission before it got right. So some things haven't changed with regards to publishers. But actually the fun thing is that I would say that the use of indentation in the way that Landin suggested, for my work at least, has been hugely beneficial in terms of publishing, because it means I can write entire programs in my papers and they don't take up too much vertical space or horizontal space, and you can sort of move things around and it becomes quite convenient. So actually the typesetting is not the problem with where clauses at all. It turns out to be a good feature from the typography perspective. Anyway, so other features of this paper are an introduction to language abstraction layers. So he says in part of his paper that there should be a very clear distinction between physical and logical languages. So what does he mean by this? He wants to extract 4 different layers of language that are important. And by physical ISWIM, he means the language that you write down and how it is written down and how it is represented. Which exact characters on the computer are you using? Which character key set are you using? Perhaps even which font are you using in the papers that you're printing is important. And maybe these distinctions shouldn't be important for a language, really, right? So he's thinking it's not a good idea to distinguish a language by the exact character set that the keyboard has, that you have access to on your keyboard. That's not how you design languages. You should separate that away. And so he talks about, well, really the idea of tokenization is being a separation of how you should do these things and the distinction to what you would call logical ISWIM. And he refers back to the Algol report and says, yes, people did this in the Algol. We did have a distinction there between the the physical representation, so there's the Algol report version and the Algol on computers. But the fact is that Landin devotes 1/10 of his paper to this very discussion. So it's clearly very important at this point to make these distinctions between the two physical and logical representations. And so it tells you something about what was going on in the minds of computer scientists at the time, which to me, my mind boggles that they had these discussions, but they did. He sacrificed a lot of time to this. After logical ISWIM, which is where we have tokens that represent what we have, he says it would be good if we had a distinction between the version of ISWIM where we're not talking about just the tokens, but rather their grammatical structure. So how are things parenthesized? And it's important to distinguish that between what's written down and this more abstract version of things, which of course is now what we would think of as the AST, the abstract syntax tree, when you parse your data type. So that's a clear win in his mind in terms of how you describe the language. And then he wants to interpret these syntax trees into applicative expressions, which we've seen previously, obviously, so he can then evaluate these and recognize that evaluation in terms of the SCD machine. So it's interesting to me that, again, that he devoted so much time to this particular idea. I think it was probably important at that time, and that today, it's almost not worth me talking about this because this is exactly how we always work with languages. But of course, it came from somewhere, it came from someone, and I think it came from Landin. At least the crystallization of this idea came from Landin. Another large part of this paper, so about a page worth, so another 10%, is really devoted to the idea of equivalences in programs. And he wants that to be, or he recognizes that there are 4 different kinds of equivalences in ISWIM that are important. So the first one is the importance of sub-expressions. So it should be that if you have some program or function L equal to L prime, then L applied to M should be the same as L prime equal to M. And similarly, for terms M equals M prime, then you want LM equals LM prime, which these are laws I've always been taught as being Leibniz laws, which comes back to what we started with in this talk, and it's quite a nice connection. And he's thinking that this should be true for all sub-expressions. And really he's thinking, he complains that in certain languages, even in Algol, even in Lisp, that there are terms in these languages which are nearly equivalent, but not exactly equivalent. And that's not right for calculation. And we really want it to be precisely the same. And so he brings in all of these different equivalences. He wants that to be an understanding of equivalence within definitions. So the use of let and the use of where, there should be an exact correspondence between these two things. They're just syntactic differences. That's important to him. He also goes on to talk about how these equivalences for let and where should also be the same thing as substitution. That there should be no difference. And then he talks about built-in expressions in the language. So here we have the conditional statements. So if true, then M else N should be exactly the same as M. And if false, then if false, then M else N should be equivalent to N. Again, this is saying something about side effects. He's saying that there should be no side effects in the evaluation of the predicate on the left-hand side, and it's important to keep that completely separate, this and for all the other built-ins that he has in his language. The fourth kind of equivalent he identifies are what he calls primitives. And it's interesting to understand what primitives are. This is an idea that isn't really fully implemented even today. At the beginning of his paper, he says this. He says, ISWIM is an attempt at a general purpose system for describing things in terms of other things that can be problem-oriented by appropriate choice of primitives. So it's not a language so much as a family of languages of which each member is the result of choosing a set of primitives. What is he talking about? In his mind, ISWIM is a general purpose language, and when you encounter a new domain, what you do is you define primitives for that particular domain, and you want to have program equivalences for that particular domain, and you would call that a new language. So the new language is ISWIM extended with the ability to talk to, let's say, databases, or to talk about parsing, or to talk about web pages, or whatever it is that the domain is that you have in mind. And so this is why he talks about it being the next 700 languages, because each of these sub-languages is a language in its own right, in its own means. But in the section about equivalences, he says a problem orientation of ISWIM can be characterized by additional axioms. In the simplest case, such an axiom is an ISWIM definition. So he's thinking of maybe you want your extension of ISWIM to be ISWIM itself. That's one form of program equivalence that you might add. But he's very sketchy on the details of what he means in section 4 exactly. I think he's trying to say that you want to be able to add equations that talk about the sublanguages, about the primitives that you have that you're working with. So, for instance, if your sublanguage has put and get operations, then putting the same value twice into the same memory cell should be the same as doing it once. That's a program equivalence that we'd like to have true. He doesn't say this, but these are the kinds of equivalences that you might want to add to such a language.
A very dangerous assumption.
A very dangerous assumption, yeah.
Because I was working for the BBC automated news studio with a group of people who programming in Corel, and the Corel compiler took this opinion, but they were interfacing to a chip made by Intel,
Okay.
where you had to give it successive values in the same memory location,
Okay.
which we would regard as instructions.
Yeah.
So they took ages to figure this out, but I figured it out immediately programming in Forth, because I could, a very interactive language, you could just do one thing and then have a look around, have a poke around. So that was that
Very good.
little story.
Yes, thank you. So yes, we want to have some form of equivalence between the primitives that we're adding to our language. How do we do that? And this isn't something that we see in languages today, really. We don't see a program equivalences being applied to new interfaces that we have. We might want to desire them, but they're not formally encoded in any way. Another big part of his paper is the idea of denotation. He says in particular that one of the important things about arithmetic and algebra is that the thing an expression denotes, that is its value, depends only on the values of its sub-expressions. So this is, I think, really foreshadowing the idea of denotational semantics, which was then later, of course, gone into much more detail by Scott and Strachey, where the value that you give to an expression is equal to the value of its sub-expressions, and then some kind of function that combines them. Which is this is from Scott and Strachey's paper, which introduced what I think people call Oxford brackets, but I think I was taught to call them either Scott or Strachey brackets, depending on what you're doing. So back to my functional versus imperative story. Well, it's not clear to me that really there's this great big divide between these two, and it wasn't clear to Landin either. So Landin says, ISWIM brings into sharp relief some of the distinctions that the author thinks are intended by such adjectives as procedural, non-procedural, algorithmic, heuristic, imperative, declarative, functional, descriptive. Here is a suggested classification and a new word, by which he's talking about ISWIM, and the new word he wants us to use instead for these kinds of language that he's been describing is denotative. So we should have denotative languages, which basically mean that we have denotational semantics at the heart of how we understand the expressions of that language. So that was the next 700 programming languages. But of course, the title of my talk is the next 700 domain-specific languages, because that's the terminology that we would use now to talk about these primitive languages that you would extend ISWIM with. And I want to just take a sidestep now to talk a little bit about my work and a bit about my perspective on this and where I come from in terms of understanding this problem. So to start with, I want to talk about lists And lists can be evaluated by folding their structure. So you have cons and nil in a list. So here's a list 2718. And the semantics of what you want to do with this list should be given by decomposing your list into its fundamental parts, so cons, cells, and empty lists. And then suppose you want to take the summation of something's happened. Okay. Then suppose you want to sum these things, then you would do 2 plus 7 plus 1 plus 8 plus 0. Well, how do you come about that? Well, you decide to replace the empty list with 0. You decide to replace cons with addition. And so we're doing something that's very structural based on the structure of the list. So given the structure of the list, you apply some transformations and you get the semantics. So this is what we call the Haskell community default right with this list. And this technique generalizes to many tree-like data types. We can replace constructors of trees with functions over those over the arguments of those constructors, and we can recurse. So the idea is that the data structure should really inform the algorithm that we're writing. And there are many, many variations in this theme, depending on whether you're dealing with mutually recursive data types, whether you're dealing with recursion with parameters, whether you're looking at some historical context, and lots of different variations. In my subfield, the world of recursion schemes, we talk about lists as being something called a catamorphism, because there are all sorts of different morphisms. So catamorphisms are the ones that destroy, that's the word cata, like catastrophe. You destroy a data structure like a tree into a single value by carefully doing some structural recursion over the entire data structure. Catamorphisms are part of an entire zoo of these things. And the zoo is truly immense. There are catamorphisms, anamorphisms, apomorphisms, histomorphisms, mutuomorphisms, and so on and so on. And with all these strange names, you might ask yourself, is there a unifying framework for all of these different beasts? And the answer is yes, it's a zoo of morphisms, and you can do a whole bunch of maths to discover that there's an underlying structure that unifies all of them. But it took something like 30 years for us to discover that underlying unification. So that unification was achieved initially by Ralph Hintze in a paper about adjoint folds, and then we later extended it to cover something called recursion schemes from comonads, which Ralph Hintze didn't think was part of his adjoint folds in this paper called Unifying Structured Recursion Schemes. And then eventually we, in 2015, along with Jeremy Gibbons, managed to generalize this further to what we call conjugate hylomorphisms. And our morphism nickname for these is that they are the mamamorphisms, because they're the mother of all recursion schemes. These ones really seem to generalize all known recursion schemes that we're aware of, and all co-recursion schemes as well. And if you're interested in learning more about these things, then I've recently written a paper with my PhD student, Zixuan Yang, called Fantastic Morphisms and Where to Find Them, a guide to recursion schemes, which was published this year, so you can take a look there for support. And really that's a look at recursion schemes, not from the categorical perspective, but from the perspective of what are these beasts and how do you use them? Okay, so why have I told you about recursion schemes? Well, I want to talk about folding domain-specific languages, deep and shallow embeddings. We saw in Landin's paper that there was very much this idea of there being denotational semantics to syntax, and from my perspective, a syntax tree plus a recursion scheme corresponds exactly to a language with the denotational semantics for that language. So if you're thinking about language as being simply given by a syntax tree, well, a recursion scheme should be able to give you any kind of semantics that's desirable from that in some way. So being a specialist in recursion schemes hopefully gives me some insight into the way we do denotational semantics. I don't want to go into the details of this slide too much. The idea is that an expression like this addition would be given or described by a tree where you have nodes that describe adding and nodes that describe variables. This corresponds to a data type. And you can write code that does an evaluation of that data type based entirely on its structure by providing what we call a base functor that describes the shape of a particular node in this tree. And then the idea is really that if we have a syntactic plus, that corresponds to the add to the stuff in blue here on the left, and then the semantics is given by some function, which we call an algebra, that ensures that you're doing things denotationally and that you're preserving the structure throughout, and variables are treated in a very systematic way. So by providing what we call an algebra, you force yourself to be denotational in the way you evaluate these trees. Now, we weren't the first to make the observation about the importance of denotational semantics by any means. And the idea of separating out or understanding program structure in terms of these kinds of data structures appears for a long time before, but at least in 2009, is crystallized in a paper by Plotkin and Pretnar called Handlers of Algebraic Effects. And their idea is that syntax should be represented by what we call a free monad over a functor that provides a signature. So we provide something that says what the monad should look like, and then the semantics is given as what they would call the unique morphism from the free monad to the semantics that you want. Well, this would be given in terms of a fold. So they've really got that there. And I want to just give you a flavor of why algebraic effect handlers are have become so useful and so popular in the functional programming community. So what are algebraic effect handlers? Really, we're saying we have syntactic, so algebraic effect handlers are syntactic in that programs are embedded into your language as just data types, as trees. They're also denotative in that you fold over these trees using an algebra. They're algebraic, which means that operations have to respect substitution and sequencing. So here we have a tree with an OR operation, and the tree is saying there are 3 different answers to this problem. It's either 2, 5, or 3. And the handler here says we can handle the OR construct by replacing each of the OR nodes with appending. So we're going to stick things together, and we replace values with singleton lists of those things. So this is basically saying, if you have a non-deterministic program and you want to know all the solutions, well, just make a list of all the solutions. So that's one way to interpret this program. But the important thing is that, I should go back. But the important thing is that the OR construct should have this equivalence in the way that it's built. So this says, if you have a program P or Q, so if you're going to do either P or Q, and you get the result X, and you continue the rest of your program with that X, that should be the same as either doing X from P followed by KX, or doing X from Q and continuing with KX. So this is what it means for OR to be an algebraic operation, that the rest of your program can distribute through the operation itself. Another feature of algebraic effect handlers is that they are extensible in the sense that rather than starting with a fixed notion of what your syntax tree is, you can extend it with new operations. So here we have the addition of the fail operation that says you failed to find a result in this branch. So there's a way of adding new programming features to, or programming language features to your tree as you go. And of course, fail has to be algebraic. It is, so fail has no continuations, no parameters. And so fail followed by some continuation is the same as just fail. We also like these things because they are modular. So in this previous slide, I gave the semantics of fail by saying it should correspond to just the empty list that says that there are no results. What we could do is we could handle just the OR parts of this tree and replace them with appends and leave the fail part alone. And then in a later part of the evaluation, handle fail by itself and then just do the replacement there. So the idea is that we can be very modular in the way we interpret languages. We can interpret each language feature one at a time, doing tree-to-tree transformations until the entire tree has been evaluated. So this is a kind of modularity that comes from these algebraic effect handlers.
So is fail or 5 the same as 5?
Sorry, say that again?
Is fail or 5 the same as 5?
That depends on your semantics. So the idea with this is that the handle function is going to decide how to interpret OR. So you could have it so that fail or 5 is fail, or you could have it so that it's 5. It's up to you to decide what you want. So that's kind of the flexibility that you get from this way of doing things, which actually I think is the next point I was about to make. So, so these handlers should be flexible. Multiple semantics can be given by giving a different folding structure over the trees. So this is the example where perhaps you want to just have one result rather than a tree, rather than have a list of all the results. Perhaps you just have one solution. But as you said, you could instead say you ignore the fails, or you could say a fail kills the entire tree. That's all possible as well. Another aspect of algebraic effect handlers is that they should be equational. So the relationship between operations should be expressed by laws that are on top of the algebraic of the algebraicity property that we have. So you might want to say that or PQ is the same as or QP. So these things, it might not matter which order that you are in your non-deterministic world, and that completely changes the semantics that you're allowed to give in the handlers. So some things will respect this law and some things will not. But I think this goes back to what Peter Landin was saying about having primitives and having equations over those primitives. This idea is starting now to be expressed in the way we're doing these kinds of handlers. Algebraic effects are very useful because they're pervasive, so they cover many different kinds of useful effects. For instance, printing, getting, putting, throwing, forking, reading, writing, a whole bunch of other things are algebraic, so they're very good for designing languages. And they're also efficient, so here I've drawn a kind of a dotted line that represents the idea that rather than starting with this tree and then producing this tree and then taking this intermediate tree and producing another one, you can immediately go from the initial tree right to the final semantic tree as well. Through some various properties or transformations, which means you don't have to have all these intermediate steps if you do it right. So they can be implemented very efficiently. And my early work in this was really to show that you could use algebraic effects to do different heuristics for product-like languages. And the idea is that you represent non-determinism as trees, and you may have different heuristics on how to do that tree. So maybe you're doing depth-first search, maybe breadth-first search, maybe you're doing depth-bounded search, perhaps you're just wanting one result. And so how do you do all these different semantics? Well, you use different handlers over these things. It's a very simple idea. One of the open problems for a long time about algebraic effects was about, well, operations as not algebraic. So we talked about the importance of that algebraicity property. There are certain operations that don't respect that. So for instance, if you want to list all of the results, then you would give this particular semantics. If you wanted just one result, you give a different semantics. And a natural question is there a general way of dealing with non-deterministic programs, which we might call a searching program, where search could be list, or could be once, or could be depth first, or could be breadth first? Is searching itself an operation? It's not algebraic, and I won't go into the details as to why not, but it doesn't satisfy the axioms of being algebraic. But nevertheless, there are equations on how we should expect searching to work. So it's equational in some way. And so the open question there was, how do we actually deal with these operations? And now we have a good story of that, for doing that in terms of indexing and having different layers of scope and being sensitive to that scope. So that's something that I did. And I want to just finish my talk now with a kind of a little case study on how theory met practice with algebraic effects. So there's this company called GitHub. They're the providers of open source repositories, or they host open source repositories for pretty much everything these days. And what they wanted to do was they wanted to have a means of doing program analysis over people's code. So people submit code to GitHub. They want to be able to do analysis on this, but they don't want to do a new version of an analysis for every language that's out there. They want one system that does an analysis that can be used for different languages. And so they thought that the use of algebraic effects was a good fit, because they could say how to work with a particular feature, or do analysis on a particular feature for one language, and then so long as other languages use that feature, they could compose features into, they could say that each language is the composition of different features, and then reuse all of that engineering. So they said, algebraic effects are nice, but we can't express lots of constructs like if statements and try catch as syntax, but they're useful in languages. What do we do? And so I said, well, it sounds like you need scoped effects, which is the stuff I've been working on. And so I showed them the paper, and they were very happy with the results that were there. And they looked into it and they said, oh, this seems to fit the bill. We're happy with this. It seems to work. But is it efficient? And so I showed them another paper that I'd written, and that shows them, yes, that there's some fusion rules that shows that you can collapse all the trees down into a single run. And they implemented this, and they were amazed. Their code base was 250 times faster than it used to. They were able to complete their analyses, and they put it out to production. And so when when you submit some code in 9 different languages and click on where the source syntax comes from, it goes to the right line in the source code. And all these sorts of things have been enabled because they used algebraic effect handlers. So that was a success. Somebody tweeted to say, did you ever stop for a moment to think how many development hours a feature like jump to definition saves a day? So that's a huge win. So we wrote a paper together showing how industry and academia could be fused together at GitHub. So that's the end of my talk. We've seen the distinction between functional and imperative. Landin thinks denotative is the right word to be using. And my question is, are effect handlers denotative? I think they are. So I'll finish there. Here's a list of references. I just want to call out Jeremy Gibbons and Jamie Willis. Thanks for looking at the previous version of this talk. Thank you.
Thank you very much, Nick. We have people online and here, of course. I think it's probably easier if we maybe ask if anyone here wants to ask a question first, and then I'll throw it open online. So would anyone like to ask a question locally? Over.
I was wondering if Church spelled out in the early days the lambda notation for defining functions was specifically computable functions, not the whole kind of gamut. I think that's right, isn't it?
I think that's right. Yes, absolutely. Yes. Yes.
Did he spell it out?
I think he spells it out quite beautifully in the second paper that I cited. So
right.
Yes. That's good. So yes. Yeah. Yes. I think Church's writing style is quite interesting. If you compare him to Turing, they're completely different. So Church is very much a mathematician in the sense that he's very economical with what he writes, but what he writes means a lot. You see that very much in his paper about the decision problem, which is just 4 pages long, and he just cites it in the paper and carries on, assuming you know everything that was in the previous paper. So he's a harder, more precise read. Turing, on the other hand, and he's also extremely precise, but there's a lot more said in his paper. I think if you read Turing's later papers, you can see Church's influence on his writing style. I think he reined him in a little bit. Yeah.
So fail or 5 could be 5, or fail or 5 could be fail.
Yes.
In which case fail would propagate up the tree and the whole tree would all fail.
Yes, it would.
And does that correspond to, in a guarded command language, one interpretation being fail is infeasibility or magic, forced back?
That's right.
And the other interpretation is that fail is non-termination.
Yes.
But why use fail for both? Why not have 2 names?
Well, that's a very good question. And I think that, so I used fail because historically in the algebraic effects community, fail is what we call that action. But Carol Morgan suggested to me that we should probably call that stop instead of fail, because it's sort of more neutral on what that means for exactly the point that you've made. And I think that's right. So non-determinism, when we think of it in terms of algebraic effects, we postpone the semantics to the handler. And so we need a more neutral term for what failure is. I think stop is a good name. Yeah. So it would allow you to say, maybe we do something angelic, maybe we do something demonic. It very much depends on the context that we're in.
That leads to another question. It must be, that's very appealing.
Maybe when you can have another.
Do you think algebraic semantics is implementable?
I'm not sure what, so the answer would be yes, in the sense that algebraic effect systems exist now. So there are languages based exactly on these ideas. There's a whole bunch of them, but is that the question you're asking?
Yeah, I'm not sure.
So I would say it's an ongoing development effort now to understand whether or not, or to how close we can get to algebraic effect languages where equations come into the story, so where we can actually quotient trees over the additional equations that are there. But the idea of algebraicity, that certainly is implemented, and it corresponds directly to folding trees. I've done that in the context of Haskell, where you think of your tree as being quite literally a data type, and then folds over that tree corresponds to the evaluation function for that, and that evaluation function is parameterized precisely by an algebra. So it's by definition algebraic. I think that's certainly true. There are languages that are specialized to algebraic effects where that still holds true, but I think it's made more convenient for the user, so they see less of the maths and more of the kind of use case of how you make these things work out. But the ideas are very much there.
Any more local questions? Otherwise, I'll open it up to online, so I hope everyone can hear us. It's probably easiest if you actually ask your question by unmuting yourself. I think there's not hundreds of people out there. So if you've got a question you'd like to ask, just unmute yourself, say who you are, and then ask your question. So we're hoping somebody might come in from outside.
Hello, Jonathan.
Hello.
This is Richard Bornat.
Hello, nice. We can hear you. So do ask your question.
Well, my question is more of a comment. And I'd like to thank the speaker for giving a Peter Landin talk, which focused on Peter Landin. I once did a Peter Landin talk without mentioning the man, and if there is a hell, I shall burn in it forever for that. You did a wonderful, I think Peter was a famously prickly person, or at least he was to me, and I think he would have loved your talk. It was a superb resurrection of the term denotative, and thank you very much. That's all my comment.
Thank you, Richard. Well, we hope Peter is out there somewhere, but yes, do respond.
Can I respond to Richard?
Yes.
So,
Yes.
Richard, it's a pleasure to meet you, even though it's just virtually. I've been reading about you and your teaching of iSwim, and actually, I was wondering, I read that you wrote a book that apparently featured iSwim heavily. Is that true? Was it really taught to undergraduates? How well did they do with iSwim?
Well, this is another thing for which I shall burn in hell. Peter and I taught a course together for various reasons, some of which are not, well, for various reasons. Peter wanted to teach it in iSwim, and I wanted it to be something that where students could run programs. So we talked in iSwim, and we showed the students how to translate iSwim into Pascal by hand. Later on, I decided that getting students to be able to prove things about their programs would help them to understand them. This was a terrible mistake. Peter correctly identified this as a terrible mistake and walked away from me. So the book, I'm afraid, concentrates far too much on program proof. It's a bubble that burst when someone else said to me, but that's not how people learn. And I realized with a rush of understanding that it was correct. So Peter was very much a person who understood and believed in functions. And I was not.
So that explains why I can't find iSwim in your book, is that right?
The word iSwim, no. You can't find the word iSwim in my book. No.
Thanks.
Well, thank you, Richard, for the elucidation. Yes,
Thank you very much.
I think Peter always looked at functional programming as a bit like Latin. I understand that it was good for the soul to be writing it on paper. All this implementation side could be maybe wasn't absolutely necessary, but obviously there were some discussions between Richard and Peter on that.
He used to call it instrumentation.
Instrument. Okay, thank you.
What is instrumentation? The execution.
Hardware was instrumentation. Sorry, I'm mistaken. It was yes, hardware was merely instrumentation.
Anyone else out there in the ether who would like to unmute yourself and just say who you are if you do that?
Okay, may I? Hello, I'm Andrei Popescu. Thank you very much for the absolutely wonderful talk. I have a question about the mother of all recursive schemes.
Yes.
Can you give a brief description of how this creature looks like? I always wanted to read this paper, but the high level intuition maybe of does it just put together many features, or is it something simple in its generality?
Okay, so it depends on what you understand to be simple. So I don't know how much category theory you know. Do you know much?
Moderate.
Okay, so the intuition would be something like this. At the heart of recursion schemes are adjunctions, where an adjunction is basically something that is an isomorphism between two sets of functions. So on the one side, you've got functions which modify the input somehow, and on the other side, you've got functions that modify the output somehow. And there's an isomorphism between these kinds of functions. That's roughly speaking an adjunction. A conjugate hylomorphism basically says that you can parameterize a recursion scheme with an adjunction so that proofs of a catamorphism that say there's interesting structure on the input side, so interesting structure on your data structure, corresponds to interesting structure on the output side instead. So that's the kind of correspondence that we're seeking. And then the conjugate hylomorphism idea shows that if you have a distributive law between adjunctions, then you have enough maneuverability to change the way the algebras are structured so that the proofs will work out more nicely, and so that you also preserve both induction and co-induction. So that's a bit of a technical answer. I hope it's giving you some insight on what I'm trying to do there. The answer is the recursion schemes all become very trivial when you look at them through the right category, but you have to understand what the right category is for each instance, and that obviously wasn't trivial because it took 30 years to get that. Yeah.
All right. Okay. So maybe just a quick follow-up question. And how does this view unify recursion and co-recursion?
Okay. So the same. So if recursion is about taking a data structure and destroying it, then on one side of the adjunction story, we're saying there's something interesting happening on the input, and that corresponds to nothing interesting happening on the input. That's just an ordinary catamorphism where all the complexity is on the output. So this is recursion. In co-recursion, it's the dual story. It's where you're producing a co-recursive structure with interesting structure on the output side, but you want that to correspond to something with no interesting structure on the output side. So that's the other side of the equation, but where all the interesting structure is now on the input. So the seed that you use to create your co-recursive data structure. So the duality is entirely preserved in the way conjugate hylomorphisms are built, because it's all about extending the recursion scheme, either by looking at the input side and changing the parameters there, which then through the adjunction gets turned into output, or vice versa. And so all the duality is preserved. I hope that makes sense.
All right. And the final follow-up question, I promise. Does this cover mixtures of recursion and co-recursion, this scheme?
So yes, to a degree. So you can have, so it doesn't cover, well, okay, let's say yes to a degree. So an example of this is the so-called dynamorphism, where you have a recursive data structure, a recursive algorithm, but with a co-recursive lookup table. So the idea with the dynamorphism is, roughly speaking, it corresponds to dynamic programming, where what you do is you build up an intermediate data structure, which is the table that you want to do your lookups in. That table could, in principle, be a co-recursive thing, and yet the recursion scheme should be terminating on the indexing scheme that you're using for the algorithm that you're writing. So you're using recursion on the indexing scheme that you have for your dynamic programming algorithm, but you're indexing into a co-recursive table. So yes.
All right, thank you. I think I'm now armed for reading your paper. Thank you very much.
Well, you're very welcome to get in touch with me if you want to talk through the paper in more detail.
All right, many thanks.
Thank you, Andre. Anyone else out there?
Yes. I'm sorry I came in late because I couldn't find the
Hello, Margaret. Just introduce yourself.
Oh, yes, Margaret West. Sorry, yes. I couldn't find the email with the Zoom link in, just an infusion of too many meetings today. You talk about functional programming languages, in your talk. Well, where does this leave logical languages like Prolog? I mean, you may have mentioned them, but I can't remember. How do they kind of fit in to your scheme?
So that's a good question. And in one of my, so in fact, in my first encounter with algebraic data structures, or algebraic effect handlers, sorry, what we did is we modeled Prolog as a system that worked over the non-deterministic trees and gave the different semantics to things like cut, etc. So I think that Prolog is at its core an algebraic language. So I think it fits quite well into this story. I think that, again, I think Landin's idea of calling these things denotative would stand here. So I think a good Prolog is one that has a denotative semantics.
I hate to say this. I know I'm stepping into the fire. But in my PhD, I think I used a denotated bits for some of it. So I'll withdraw that. Forget I said it. But I must this is a bit trivial, really, but I must say I did do some Lisp to solve a rota problem. It was a hospital rota problem. Somebody suggested an algorithm way of doing this, and I mean it was brilliant in that, you know, as a time map, I think you can more or less anything you want to do. There's a Lisp program for it. You know, you don't have to. You know, you don't have to kind of worry about it. You can find it. It's like a huge, you know, array of you know, solve anything really. But yeah, so sorry. Yeah, okay, thanks. That's it really. You say it does fit in. Yes, and of course, I think
yes,
it does.
Yeah, I think it fits in quite well.
Yes.
Maybe the wrinkle in the story is in Prolog we have the cut operation, and we have you want to be able to say there's a call, and under the call there's a cut, which kills off any siblings to the right of the cut.
I never use cut. No.
Yeah, well, so actually, that exact example is what led me on to try and generalize algebraic operations, because it's a bit annoying that the call operation itself doesn't seem to be algebraic, and yet it seems so useful, and it seems to have a denotative structure. And so that generalization of that particular operation then became what I now call scoped effects rather than algebraic effects. So it's a larger class of effects than algebraic ones, but it does cover things like call, where there seems to be some interference with the way that it deals with the algebraic structure underneath. But actually, if you view it from each call that you do, so you can have nested calls, they bring in sort of an indexed structure that allows you to do something algebraic with respect to those indices. So it did sort of spark off a nice area of research looking at that particular question.
Well, yes, cut was a no-no.
Yeah.
Cut was a no-no, absolutely not. No, thank you.
Yes, that's right. So it's not algebraic, and yet it's still denotative. So that's an interesting discussion.
Thanks very much, Hugh. Thank you.
Thank you very much. Anyone else out there in the ether, just unmute yourself and introduce us.
Can I have a second go?
Yes, of course you can, Richard.
Oh, with the camera this time.
One thing about Peter, which in his lifetime I found very difficult to understand, was that he was resolutely against typing in programming languages.
Mm.
And that, I think, was because the type lambda calculus is so much less expressive than the untyped lambda calculus. And he was perhaps in the 700 programming languages, he was looking for a way of around that. Now, I ask with similar trepidation to Margaret, would your work be able to satisfy him that you were able to express anything he could say in the untyped lambda calculus, or are you tied to the earth like the rest of us? Did you hear that?
That was pointed at Margaret, was it?
No, it was pointed at you.
Oh,
yeah.
In your system, are you restricted to things that you can say in the typed lambda calculus, or can you handle the untyped lambda calculus just as easily?
Good question. So here I would very much disagree with Peter Landin and say I absolutely want types, and I found his note on integers being round numbers very peculiar. So thank you for clarifying as to why he would write that in the first place. I think the answer to your question is, I think it's yes, you could probably do things like this. So I think you can embed, if you wanted to, you could embed types into the syntax of your language, and then you could write an effect handler that does things like say, like ask, is this the right type? Does this unify with this thing over here? You could sort of make an oracle that gives you the right information there. So you could embed things in what I would think of as being an untyped tree. So yes, I think you probably can, but I'm really saying that with my finger held out to the wind, hoping that I've got the right currents. So I'm not certain is the answer, but I suspect the answer is yes.
Thank you.
I think you end up doing quite a lot in Prolog, because you don't have types, but you quite like some types.
Can I ask another supplementary question?
Yeah, yes, Margaret.
Something which isn't doesn't seem fashionable now for some reason to use functors in Prolog. Everyone's keen on this answer set programming, seemingly, and they turn their noses up at functor. But functor expresses types very nicely, in my limited opinion.
So that's not something I'm familiar with. Did you say front?
It's for, you know, it's for matching. Oh dear, is it called functor? I don't know. It's called functor, yes. It's for matching. You can match, so you can sort of generate a type by calling them sort of, I don't know, G, which is you know, a constant, brackets uppercase X, which is a variable. So G of X could stand for the mother of X, or you know, or it can stand for, so you can put, that sort of generates a type, as it were. You can use it. I'll have to admit this. We did a group of us. We did a project on aircraft. The distance between two aircraft, was going to be dangerous. So we have the aircraft when they're flying over the Atlantic. It's too far to have the normal system, the radar. So they have to plot a path for them to go over. And two aircraft, are they in conflict or not, for example? We had, of course, lots of types in that, because there was there was feet and there was distance type, and then there was sorry, it's too long ago to remember the details, but anyway, we had to have types in there, and we model them using functors. As I say, it's too long ago to go into too much detail, because I can't remember clearly enough. Yeah, so I'll send you the paper if you like, but I don't expect you to read it if you don't find it interesting. So I'll send you a copy.
Thank you. I mean, thinking about the whole issue of types, and I think I find it peculiar that Landin didn't like types, because I mean, I can see it from the perspective of thinking of types as being a restrictive feature that bans you from doing stuff. But actually, that's in Conor McBride's words, what types are against. But what are types for? And types are for describing algorithms over the data structure of things, where you can follow that data structure nicely. So generic algorithms that allow you to do traversals are entirely guided by the types that we have in play. And so removing that language really removes your ability to write programs automatically. So I think, well,
we did do some useful things. So what they want to do is to place types by the functors by predicates. But as we had embedded types, one inside the other, that would have made something very, very cumbersome. Anyway, it's all there. So I'll send you it. I probably misunderstood something you said, but I will send you a copy, and you can read it if you have time or whatever.
Thank you, Margaret.
I wonder if Leslie Lamport and Peter Landin would have got on well together, because they seem to have similar. I presume they never met, but it would have been.
You missed lots of bits of history out, but we would have to argue about that much later. Part of Peter's career, for example, was trying to persuade John McCarthy that he made a serious mistake in the design of Lisp, but which was only corrected in the 1970s.
Well, sometime you're going to have to correct your previous talk, Richard, and tell us all about the missing parts of Peter's history and so on. Anyway, is there anyone out there in the ether who hasn't asked a question yet but would like to? In which case, do unmute and just introduce.
Timos's here. Hello.
Hello.
Peter.
Hi. Thanks for the talk. Yes, very, very enjoyable. I was intrigued by the comment about GitHub at the end.
Yes.
Now, I'd recently read a blog post about precise code navigation on GitHub, where they claimed to be using things called stack graphs in their static analysis of GitHub programs. Is that at all related to these algebraic effects?
I don't know if the current way they're doing things relates to that, but the code navigation that they had at some point was based on a library they implemented called Semantic. And Semantic was exactly based on the stuff I've been describing today. One of the libraries that they used there was something called Fused Effects, which is based on my paper about fusion for free. So I don't know about the blog article that you read, but I do know that code navigation was live using algebraic for a while.
Yeah, this was very recent, I think in last year, and they've done it so that they analyze Python, I think with precise name binding, also including cross-package references for all Python code on GitHub now.
So I'm aware that they achieved that with algebraic effects. Whether that's still there, yeah.
Okay, it'll be interesting if there's any connection there. Thank you very much.
Well, thank you. Anyone else out there who'd like to, who hasn't asked a question, would like to just unmute? Okay, I think that's probably exhausted everyone. I remember doing this once with a very early days of going around at, I think Bell, going around different, California there, no, everyone's left, etc., etc. But anyway, thank you very much. That was very nice questions. That was a very nice talk. Anyway, thank you for all of you who are out there. I wish everyone a happy Christmas who's out there and everyone a happy Christmas here. I'm afraid we're going to enjoy a glass of wine here. So if you're at home, do open a bottle and we'll be thinking of you. We're also working on talks for next year. And we do have a new seminar organizer, Alvaro, who's here. And he's from York. He works with Anna in York, and we're hoping that we'll have a fuller set of talks. They're probably going to be quite a lot of online talks, because for this talk we've got far more people online than have turned up here. So we're going to do that a lot more, I think. But we will continue with hybrid talks as well. So look at our webpage and be on the mailing list, and we'll be sending out information in the new year. Suggestions for talks are very welcome. So I'll be emailing out Alvara's email address and so on the FACS mailing list. So you're welcome to contact him directly once I've done that. You're allowed to suggest yourself, by the way. So that is fine. If you've got some interesting talk that you'd like to give, do suggest it, and we'll obviously discuss that. So we're hoping to have up to about 6 talks next year if we can. That's the idea, and at least 2 or 3 that may be a hybrid. And we may be doing at some point joint talks with the Edinburgh Mathematical Society, which Tim Denver's talking to at the moment. That may not be, maybe in a year or 2, but that's one option, which we would hope would be hybrid. So those of you who are up north of the border will be able to attend that physically, and the rest of us can join online. And Alvara's at York, so we may well have a hybrid meeting there. So we're hoping to move around the country a bit more maybe than we have done in the past, where we've been very London-centric. Anyway, thank you very much to all. Hope to see you in the new year. Thank you.
Jonathan, have you any idea of the size of the online audience?
I think it's about 30 something. Yes,
20 right now.
20, yes, it's gone down a bit.